Hello class. So on this video, we're going to cover the last section of material that is coming in on the final exam or exam 2. It's not comprehensive. So it's just chapters 4 and then chapter 6. Right? So 2 chapters and that's it. Okay. So that doesn't mean that I'll stop uploading material. There's, like I mentioned in previous videos, there are a couple things that I want to talk about, which won't be required. You don't have to watch them if you don't want to, and they won't come in the exam, but there are good applications of things we've seen before, like how to solve differential equations using power series of functions. Or how do you set up a differential equation in which you're not trying to solve one equation at once, but several differential equations at once. You can actually use linear algebra and matrices to set up solutions to things like that. Okay? So I'll talk a little bit about that just to introduce you to the topics if you want to see them. But again, in terms of the exam 2, this is the last topic we're going to cover. Right? And this is section 6.2 in the book. 6.6 in the book. Chapter 6, section 6. Now, we're going to be talking about this topic called the convolution of functions. So first, let me define what a convolution is. It's just defined as an integral, right? So it's not very complicated. Right? So a convolution of a function f and a function g, which we're going to denote as f asterisk or star g, right? It's given by, and notice it's going to be a function of t. Right? So f star g of t equals the integral from negative infinity to infinity of f of tau. Right? So it's just a dummy variable tau, right? Times g of t minus tau d tau. And again, this is a function of t, just like with the Laplace transform, because we're evaluating with respect to tau. So assuming that this integral exists, right, the taus are going to go away, you're going to be left with a function of t. Right? So that's why we write it as a function of t. Okay. So this is assuming the integral exists. Now, for our purposes, since we're really only working with functions defined for t greater than or equal to 0, we can rewrite this definition to suit our needs. Okay, so for our purposes in this class, we're going to think of f star g, or the convolution of f of g, as just the integral from 0 to t of the same thing, f of tau times g of t minus tau d tau. So again, notice this is going to be a function of t because we're integrating with respect to tau. Now, I gave you first a definition in its most general form because this is how you're usually going to see it in a lot of applications. Right? But again, for our particular case, it's fine if you just write it as a definite integral that's not improper. So just 0 to t. Right? That's all we need. Yeah. Now, there's a couple ways of how you want to interpret this convolution integral. So for us, or this convolution of functions, for us, we're going to use it to help us solve differential equations. Another way, so in terms of other applications, you can think of this as sort of a weighted average. Right? So you can think of an integral in general as some sort of average. If you took Calc 1, you should have remembered this theorem for the average value of a function. You can calculate it using an integral. Right? So you could think of the convolution of fmg as a weighted average, right, of the function f with the function g of minus tau at a specific time t. Right? So that's what I wrote here in this paragraph here. That's one way you can think of it. If you want to think of it just as an average, just using this average value of a function theorem. Now the way that I've seen it the most and how it's come up for me in my classes is if you think of an integral, of the convolution as something that's modeling a system that depends not only on a present state but on previous states as well. Right? Why? Well, look at this expression. You have f of tau times g of t minus tau. Right? So you can think of this as you have some sort of system which has a state, f of tau, right? But it's also dependent on what's happening before, which can be represented as g of t minus tau, where g could be f, doesn't necessarily have to be f. Right? This is how I've seen it show up in my class. So I've seen it show up in probability theory. We're talking about neural networks, right? So it shows up a lot. Right, in this sort of context. Right? So usually that context where the state of your system not only depends on the present state t, but on the previous states as well, is what we usually call a hereditary system. Okay. Again, when you take more advanced classes, you might see this show up. For our purposes, again, you don't really have to worry about both of these interpretations. I give them to you so you know where this comes from in applications. But for us, we're going to focus on this specific application being how can we use this convolution, or how does it arise in terms of solving differential equations. So first, let me give you some properties. So the convolution satisfies some nice properties. First of all, it's commutative, meaning that f star g of t is the same as g star f of t. So a lot of times, I'll actually be working with this definition, but both things are the same. Whether you have the t minus tau in terms of f or the t minus tau in terms of g, they end up being the same thing. It's also distributive with addition, meaning that if you have f star of g1 plus g2, it's the same as saying f star of g1 plus f star of g2. It's also associative, meaning that if you're taking two convolutions, so if you're taking f convoluted or f star g first and then doing star h, that's the same as doing g star h first and then doing f star that afterwards. So it's associative. The final property that I want to talk about is the zero property, meaning that no matter what f is, f star 0 is always equal to 0. So you can think of the convolution as a sort of multiplication. You can think of it that way. It doesn't satisfy all the properties of multiplication, as we'll see in an example, but you can think of it that way. So star is an operation. You define f star g as this integral, and then you say, okay, what properties does this integral or this operation satisfy? And we've shown here, again, I'm not proving them, I'm just giving them to you, but we've seen that it satisfies these properties. Commutativity, which multiplication also satisfies. Distributivity, again, multiplication satisfies distributivity. Associativity, again, also satisfied by multiplication. And the zero property. Again, anything multiplied by 0 is equal to 0. So in a lot of ways, you can think of a convolution as being similar to multiplying. However, it's not the same. You can see it obviously from the definition. It's not the same, doesn't have the same properties, but we can see explicitly how it's not the same. Right? So find the convolution of f of t equal to cosine t and g of t equals 1. So we're trying to find, so let me write it in terms of the star operation, we're trying to find cosine of t star 1. What is this equal to? Now, this is an example of why this is not the same as multiplication in terms of what properties are satisfied. Well, if this were as multiplication, you would think of cosine t star 1 to just be cosine t, right? Because at least as of now, this operation is behaving a lot like multiplication. Right? It satisfies a lot of those properties. But let's work this out using the definition and see what it is. You'll see that it's actually not equal to 1. Okay? So first, let's use the definition. This is by definition the integral from 0 to t of cosine of tau minus t times 1 d tau. Oh, oops, sorry. T minus tau, not tau minus t. So I'm just using this definition, and I'm using the one on this part. They're the same by commutativity. So it doesn't matter where you put the t minus tau. So I'm just putting it on cosine. Okay, so let's evaluate this. Of course, 1 times anything is just itself, so we get the integral from 0 to t of cosine of t minus tau. Okay, so now d tau. Now this is just a calc 1 exercise, right? So just find an antiderivative. 1 is given by sine of t minus tau. So this is sine of t minus tau, evaluated from 0 to t. And what do we get? Simplify this, you just get sine of t. So here you see that it's not necessarily the case that cosine or a function, so more generally, it's not necessarily the case. So we saw an example here, but more generally, f star 1 is not necessarily equal to f. And here I gave you one example, and almost always it's not going to be the same. So it behaves a lot like multiplication, but not entirely. And here's an example of why it doesn't behave exactly like multiplication. So that's the convolution. Again, it's a very, very, very simplified view of what a convolution is. Basically, I just gave you the definition, right? Some interpretations of how you want to think of where it arises, and some properties. So again, it'll show up in, if you're taking more advanced engineering classes and physics classes, probability classes. So if you're doing statistics, you might see this as well. Yeah. But again, we're not going to focus on that. Our purpose is going to be, how do we use this for solving differential equations? And the way we do it is by theorem 1. If big F of S is the Laplace transform of a function little f of t, and big G of S is the Laplace transform of a function little g of t, and assume that they both exist for s greater than a, greater than or equal to 0, then f times big F of S times big G of S is the Laplace transform of exactly the convolution of f and g, little f and little g, for s greater than a. Okay. Now, a lot of times we're not going to be taking the Laplace transform of an integral. Right? Remember, the convolution is defined as this integral. Right? So the real usefulness of this is when looking at the Laplace inverse. Right? If we have a product of functions of s, and we want to see what the Laplace inverse of that is, well, by this theorem, this is just the convolution of f and g. So what's going to happen is, whenever you have a product of functions, and you have a big F of s and big G of s, so functions of s, as long as you know that those are Laplace transforms of other functions, then you can actually find the Laplace inverse of a product, and it ends up being a sort of product. It's not the product of f and g, but the convolution of f and g. Right? But it's still very nice, right? Again, as you noticed, or as we saw in the previous slide, f star g, or star s itself as an operation, behaves a lot like multiplication. Right? So that means that the Laplace inverse of a product of functions is almost the product of little f and little g. Right? Almost, because it behaves a lot like it, but it's not equal to it. Now, we know that this inverse is unique as long as f star g is continuous. So what are we going to be using this convolution for? Well, we're going to be using it to write the Laplace inverse of products of functions of s. Right? That's going to be the idea. So we're going to do that in the next video.